Good evening, everyone. For those that didn't attend last time, I'm Tim Sepula. We'll get to that in a second. It's a pleasure to see you guys. For those that were here at the first one, I can't believe you came back for more punishment. So that's so. As promised, we were going to make this presentation about cooling towers. And the first one was about boilers. Anyone that missed it, I believe it was filmed. And certainly reach out anytime if you guys want to talk about that subject in more detail. The agenda that we prepared here tonight for you is to, again, we always start off with a safety moment. We'll get done with the introductions, go to that. And then I wanted to add this bullet point for you guys and just ask the question, has anyone seen something out there in the field that they didn't really, at the time, you know, maybe it was like, okay, we got to deal with this, but then you stop, you ask a question, you're like, why did that happen? So in the event that there's something that you saw that you didn't understand, or that you saw and you thought, hey, you know what, that would be good for everybody to hear about that, we'll go ahead and we'll bring that up and give you the opportunity to talk about that for a second. From there, I'd like to examine what the goal of water treatment is, just to kind of set the stage, and then look at corrosion, deposition, and microbiological growth. Not a knock on anyone's religion, but what I consider the holy trinity of water treatment relative to cooling systems. I just think that that's the best way to summarize that, right? When you go from there, we'll take a stop at Legionella, because that's always a hot topic. And then we'll look at how we get away from causing all the issues that we look at first. And then from there, we'll review the training objectives, make sure we didn't miss something, and then I'm sure we'll get into our heated and very long discussion at the end. As we perform the introductions, to anyone that hasn't gotten food yet, feel free, fill a plate and, have something to munch on while we go through this. And we'll kick it off here and just reiterate, Optimal Group USA is the name of the company now. We've rebranded it because we bolted on some divisions to the company that do more than just water treatment. It's all related to it, but for example, industrial services, we can perform insulation work for chillers or boiler systems. Environmental solutions, we could sell you anything from a deionized water maker to, an RO, water softeners, anything that's related to filtration or any kind of equipment like that. And we can also help you design the pre-treatment train if it would be for, say, a boiler. We can help you select which equipment it would need to be. Fluid solutions, certainly a bit of oil and gas there, and then bulk commodity chemistry. If you guys wanted like a tanker truck of bleach for some reason, yeah, they'd sell it to you. And then Optimal Water Technologies, that's the company that's presenting to you here today, the one that does chemistry, the one that provides the solutions relative to chemistry and applies them, and can help you get back in between the ditches should you find yourself off the road. Okay? All the companies headquartered just here out of Abita Springs, Louisiana, and we go pretty much across the Gulf Coast all the way as north as New Jersey now. Yeah, because if you think parking sucks to pay for here, buddy, head up there. Yeah, really shitty. So yours truly, as promised, about 35 pounds ago, because I'm getting into the summer groove here and dropping a few pounds, but started in the Navy, went to work with Nalco and then GE, ran a lot of the technical work there with General Electric before they sold that division. Was fortunate enough to meet my current business partner, Justin, and I. We started the company, about 8 years ago now, and since then, have been building it out and helping people with, well, really all their problems. Nobody calls just to say hi or talk about something fun, right? It's always, hey, you got an issue here. Yeah. But you know what? What's that? I get it, but it's more often than not, when the phone rings, I'm like, all right, what are we getting into? But we love it, and we're here for you. Call anytime. Some people do. 3 a.m. one time, in fact. Yeah. Come to find out, though, they thought they were calling a different Tim because they were at like a golf event thing. But I said to him, I said, Connor, this proves we will actually answer the phone, you know? So, without further ado, if there's nothing for introductions, we'll hop into the safety moment here. You know, the safety moment here, I think it's prudent to tee it up for cooling towers is, you know, anytime we are storing certain chemistries next to others, we have to think about exothermic reactions. Should they inadvertently mix, things like that? And even when you look at your testing reagents, wherever you have them, those things are not always playing nice with each other too. So going beyond just the chemical tanks and drums that you might have out in your plant, think also a little bit about where you store your reagents, because there's a better chance you're going to spill one of those little bottles than that big 55-gallon drum, right? Unless you got some idiot with a forklift going nuts, which happens. We've seen it. But, you know, getting a little butterfinger as you're grabbing that little, you know, buffer or something like that, probably a higher propensity. Just for anyone that likes to nerd out on it, that is salt and oxygen under the right conditions. That's what will happen. So that's pretty cool and scary all at the same time when you think about it. And why you should be careful should you ever find yourself in a barometric chamber. Probably not the best place to light up a cigarette, right? So when we look at this and we think about that, I just like to reiterate, you know, be mindful of where you store your stuff and what you put next to each other. Anything on safety before we hop into the training objectives? All right. So goals tonight is to understand, you know, let's put a definition around the goal of cooling water treatment, understand how corrosion, deposition, and microbiological growth are a trinity of sorts, how that all impacts the cooling towers. We'll understand a few facts about Legionella, and there's some doozies, right? Like, it's sexist. You know, it will impact men at a rate of like 2 to 1 over women, right? It's pretty funny. But anyways, we'll get more to that. How CT corrosion inhibition works, how the CT deposition is controlled and achieved, and then last but not least, the microbiological piece. Okay, so mention this in the prelude. Is there anything out there that you guys have seen, a question, anything relative to cooling? I'd like to limit it to that just so we don't get too far off of the subject. Anything anyone wants to bring up? If not, we'll jump right into it, but wanted to open it up and just make it, you know, put it out there. No? All right. If you change your mind, let me know. All right. So water treatment goals, what the heck is it? We're trying to maximize the cycles of concentration. We want to minimize chemical and water use and maintain the heat exchanger life and make sure we maximize the heat exchanger or the heat transfer efficiency. That's a lot of crazy words. And throughout this presentation, I want to unpack a lot of that, cycles of concentration. I hear folks talk about that in many different ways. It's fairly common, fairly basic, but let's revisit it just to make sure that we have a foundation to build off of as we go through a few of the other items. And then from there, we're going to look at what it means to truly minimize chemical without doing detriment to your system. And then look at, you know, what should we be focused on when we're treating a cooling tower? Is it just, we got to make sure that this cooling tower is functioning the right way? Well, yes, but at the same time, we can't forget about what the cooling tower serves. In heavy industrial applications, that's going to be a heat exchanger, possibly a plate and frame, shell and tube, some kind of apparatus that's responsible for transferring a buttload of heat. But in a smaller space or in a commercial application, something where we find ourselves, maybe possibly here, obviously, we might have a different need where we're serving the chiller. Either way, the heat that's generated at that maximum skin temperature, that point of the greatest heat transfer, that's a critical spot in our system. And we need to pay homage to that when we're designing a cooling tower treatment program and understanding how to operate all this equipment. So we're going to just touch on that a little bit as we get into it. Okay, so without further ado, the Trinity. Corrosion, deposition, and microbiome. In my mind, right, amongst all the voices talking, this is how I see cooling tower treatment. And I want to point out the interdependent relationship between all of the three. When you look at it, biofouling can lead to deposition. it can lead to corrosion. Just the same way that deposition could lead to biofouling, or it could lead to corrosion. What does this tell us? What this should communicate to us is that you cannot partially treat a cooling water system. You're either in it or you ain't. So if we're not doing something to address biofouling, deposition, and corrosion, we're truly doing ourselves a disservice. Okay. So let's look at corrosion and start breaking this animal down piece by piece. I'm sure that everyone remembers the basic battery cell. Just to touch on it, in case we're a little rusty, the corrosion cell is very similar. We need 4 things in order for this to exist. We must have an anode, a cathode, an electrolyte, and an electron flow. An electron flow. Now, what does that look like? Okay, let's pretend that the gray blob at the bottom is the pipe wall. This is the water. Seriously, the best picture I could find, guys. And if you look at it, the anodic area and the cathodic area are going to gain some significance here. So we've got 4 things we got to unpack. The anode, the cathode, the electron flow, and then we must have, as we said a moment ago, our electrolyte. So our electrolyte is the water. Our electron path is where material is moving from the anode to the cathode. At the end of the day, what does this mean? It means, if we think about it, some chillers have sacrificial anodes, right? Okay, what is that doing? We're telling the machine that we understand it wants to corrode. And we're hoping that we can bribe it into corroding there, right? So we put that anode in there because we expect it to exist, and we hope that it sacrifices that piece that we can change out before it attacks our tube bundle, our shell, our channel head, whatever that piece of metal is on the asset that we don't want to have go away. It's also good to point out that if you look at it, metal dissolves always at the anode, and it deposits at the site of the cathode. Why is that significant? It's significant because when we get to the point where we chemically treat to stop corrosion, we have to block the anode and the cathode so that we can take out the potential, reduce that corrosion potential. We can't get rid of the water, kind of handcuffed. Cooling tower needs water. This electron path is going to exist. Shit's got to move. But what we can inhibit is the anodic area and the cathodic area from wanting to corrode. Knowing that it still might happen, you might find that you have sacrificial anodes. For those of y'all with fishing boats that are going in the marsh or something like that, your sacrificial anode on the back of that boat is what? Zinc. You put a puck on it. In freshwater, where we don't have any brackish, any signs of salt, we would use magnesium. And that's typically what you put in the chillers. At least it would work best out of the 3 most common: magnesium, aluminum, and zinc. Okay. Okay, so that's how corrosion works in a nutshell. So once it exists, that's how it's going to happen. We're going to dig a hole at the anode, and we're going to make a deposit at the cathode. And in the Holy Trinity, where we said, hey, all of these actually are interrelated, we now understand that corrosion occurs, corrosion products deposit at the cathode from the anode, and now we've created habitat. And that habitat leads particle entrapment at the site of deposition, and now we get some funky things growing in that little piece of gradu that is now stuck to our pipe and is going to drill a hole and cause a failure. So let's look at a few other things that influence corrosion. The 4 things that I'd like to touch on, 5 arguably, are pH. You will see, very basic, that the corrosion rate will increase as the pH is lower. As the pH increases and gets more caustic, basic in nature, the corrosion rate tends to go down. This is why we don't mind when your cooling tower pH is upwards of 9. The scale for pH is 0 to 14. Anything less than 7 is considered slightly acidic to very acidic as you get lower and lower. 7 is relatively neutral. The water coming out of our parish here in New Orleans, or Orleans Parish, is going to produce about 8.4, 8.5. At times, it could be upwards of 9.2 pH. The Mississippi River is the water that they're pulling and treating and then sending to us as city water finished, right? So anytime that we have Mississippi River water as the source of the influent water, we can expect to see a very similar makeup. What's nice about that, though, is we see that naturally our water doesn't like to corrode things all that much. But still, there's some other things that we have to worry about. So, just to put it in realistic terms, relative to corrosion, the Mississippi River water that we get as city water ultimately is not terrible on its own. Easy to work with. Now, oxygen and temperature. It's important that we put these two things together because they're a terrible couple. They fight a lot and they make each other worse as a couple. As oxygen increases and temperature increases, your corrosion rates go through the roof. At 120 degrees Fahrenheit, the only word that I can use to describe it is oxygen will become nascent, insidious, awful, demonic, and it will literally drill like a drill bit through the metal. It's terrible. It's a little bit more prevalent in boilers because of the temperatures, obviously. But where you have high heat exchange surface temperatures on your chiller, maybe you have 110 degree skin temperature. At that point of the highest heat transfer, where oxygenated water, you better believe it's oxygenated because that cooling tower is a huge air scrubber, so max saturation of oxygen already present, right? Now you heat it up, and that oxygen is going to want to tickle that metal in a bad way. And that bad touch is going to lead to pitting. And we got some pictures, because I think pictures are worth at least 10 minutes of me talking. So we'll get to that here in a minute. Conductivity is the other thing that will influence corrosion rates up. As we increase dissolved solids, corrosion potential increases. Did anybody do that science experiment that I know I did because, you know, it's fun? You take that tank of water, pure water, put the light bulb over here, drop the toaster in this end or the cord, whatever you got, and it doesn't light up. Put a little salt in it, and all of a sudden it lights up. This is that principle. If you have pure water, it's not conductive. It will not conduct electricity. You will not kill your spouse for the insurance money. But if you put some salt in the water, it'll go there. And you will get higher conductance, which means also for metal that you can increase the corrosion potential, which is why we utilize conductivity as one of our metrics most commonly, to make sure that we don't exceed a certain value, which then bad things start to happen, not only to the metallurgy, but also to things like deposition, things like corrosion, which, again, they're all interconnected. Okay? So, last thing we want to touch on is velocity. It's a weird shaped graph. That's because there's two kinds of flows. I'm sure that a lot of you are familiar with turbulent flow and laminar flow. And that's the reason for this little peak. In that period of time, there are some things that are happening. And it has a lot to do with the dissociation of H2O, hydrogen gas, and creating a bit of a blanket that protects the steel. The biggest takeaway is oxygen polarization is going to help you for a couple of minutes. Then you're going to get to a certain velocity where it's going to work against you. And then you're going to get to another velocity, it's going to take off, and then you're just not going to have a copper pipe anymore. So, velocity is a big thing that we have to also consider. It's not always a chemical solution. And for those of you that remember the boiler training, I mean, it's a bit tongue-in-cheek to say that chemical is not always the answer. But truly understanding how a piece of equipment was designed to operate and how it is being operated give us the ability to draw the box that is chemical treatment around that particular application. But having a known set of standards, understanding the piece of equipment and how we operate it, is going to do a lot to make sure that we're not punching ourselves in the face relative to some of these very low-hanging fruit items, such as velocity and some of the things related to temperature that might bite us in the ass if we don't give them the proper respect that they're due. Okay. Any questions on this before we get into the pictures? Types of corrosion. These are probably the ones that you will see the most in a failure analysis report, and certainly the ones, because they are the most prevalent, that you'll notice should you take down your pieces of equipment for inspection. You'll probably tend to see these a lot more than anything else that's a little bit more of a, well, a mechanism that's probably because of what you have going through, the fluid mediums, right? So when we look at what happens around here with these types of systems, uniform corrosion, pitting, concentration cell, galvanic, I would say that those are going to be the ones you see the most. Leaching, you know, there's just not a lot of brass that's out there anymore, right? Copper nickel, prevalent, 70-30, copper nickel. But as far as brass goes, we don't see that as much anymore in materials of construction on a lot of these builds. But when you do see it, or if you're a trumpet player, there's something to be said for that, and we'll go through it. Stress corrosion cracking or microbiological, those are the last two pieces. And, you know, stress corrosion cracking, under the right circumstances and a little vibration, it can take you offline really quick. That's a very short-term failure. We'll talk a little bit about the time to failure as we go through them. If you wanted to have a type of corrosion, if you were like, okay, I get it, it's going to happen, which type can I actually say, okay, uniform corrosion would be that item. Uniform corrosion is baked into pretty much every one of the engineering design rates utilized. When they say that we anticipate the end of life on this piece of equipment being 20 years, 30 years, oftentimes you will find a mil per year value of corrosion that they expect over that span of life. So, when you look at it, this is easily measurable. General corrosion exists pretty much in every system. And the reason why corrosion wants to exist is because everything was forced to look like a pipe. We don't go out in nature, dig in the side of the mountain, and find a damn piece of pipe. What we find is ore, we smelt it, we form it, and from the moment that it exists as a piece of pipe, it is trying to fight its way back to being powder in a rock. It doesn't want to stay in that form. The molecular structure has been swayed, it has been abused, and it wants to corrode. Expect that uniform corrosion will be a part of your application. And uniform corrosion, we can control. Any questions about this before we get to pitting? Pitting, on the other hand, is the first of our insidious, awful, terrible types of corrosion. We give it the front stage here because pitting corrosion is hard to detect. Think about it. Oftentimes, this is going to be localized. You would find it in an elbow. You would find it in a portion of the system, not the entirety of it. And if you are pitting in a small little spot in a localized area, it is going to dilute the iron or whatever that piece of metallurgy is. And it is going to be hard to detect through you guys' testing or our testing. Pitting corrosion usually bites you right in the rear end. And you find it, hopefully at inspection intervals, before it causes you to come down offline in an unplanned outage. If you have corrosion coupons in the system, of which this is an example of a corrosion coupon, those are tattletales. And hopefully your company that you have, if you're not working with us, shame on you, but if you're not, I get it, it happens. In that case, it is good to make sure that those folks are checking these on a weekly basis visually. Might send them in at a 30-day, 60-day, or 90-day interval for a formal analysis, but a visual, you want to make sure that that visual analysis is a general corrosion look. If you start to see pits and little pinholes in this, you're going to want to start taking some action, because somewhere in your system, those pits can exist. Certain chemistries and the use of them in certain systems that are aggressive are specifically added to stop pitting. Pyrophosphate is a perfect example. We'll get into that later. Okay, so pitting's awful, and it is probably the worst type of corrosion that you can have. Let's go to something now that should hit a little closer to home. Concentration cell corrosion. Everywhere in your system, you have this size pipe, it goes to this size, and then it goes back down to this one. In those instances, you have flow paths. If we were to think about the Grand Canyon for a moment, and all of a sudden we unleash a rush of water through it, and that water is traveling and it's hitting this particular rock, and now it's being diverted that way, that's the same thing that happens within our piping systems, correct? It is. And as we go around those 90s, as we come to splits in the line, and that flow goes this way or that way, now we have a certain situation that might be brewing. The electrochemical, electro-corrosion mechanism can be different in certain spots relative to that flow rate. It can change the way that the anode and the cathode move, because there's not just one, there's billions of them. Anode, cathode, anode, cathode, anode, cathode. They're just everywhere, right? They're thick as hair on dog's back. And as a result, in some spots where you have lower flows, or you have different concentrations of the same medium, water, but maybe it's a little more cycled there than it is here, this is going to exist, and why you will find when you take the bell end of a chiller off and you see different depths of this corrosion, of that corrosion, oftentimes it's related to this. The other thing that it could be related to, the reason for these pouty lips on these particular chiller tubes, is galvanic corrosion. If the water chemistry does not support inhibiting the corrosion of both yellow metal and ferrous metal, mild steel, the way that it should, then you run the risk of having corrosion and dissolution of the copper and the steel, but right now we're going to focus on the copper. When that copper lands on the steel, in that spot, it starts drilling through the steel. That's this corrosion mechanism in a nutshell. It is terrible, and it's insidious, and it's awful, just as bad as pitting, because really, we're creating pitting. This is why when we look at corrosion of yellow metal in a system, we can't just focus on the chemistry being the only thing that solves that issue. It goes back to velocity as well. One of the other things that we talked about. Specifically, going above 8 feet per second velocity through a copper pipe or a copper nickel pipe will encourage erosion corrosion. The velocity will start to rip apart the pipe and start depositing little pieces of copper on the steel and start this type of corrosion. You will see the droopy, pouty lips of the pipes. That's the copper going away. Everything else around it are the little drills where this galvanic corrosion is occurring and is just drilling through it at a rate that is oftentimes terribly accelerated. 5x, 6x, could cause a piece of equipment to need significant change out of components in as soon as years. Okay. I made the comment a minute ago about trumpet players being interested in this in addition to all the water treaters. The reason is, and I learned this from a gentleman that actually played the trumpet in one of the presentations, he goes, man, it looks like my, the spot that I put up to my lip. Reason is, our saliva is acidic in nature. And so as it interacts with that brass piece on the horn, over time, somebody who doesn't change out their pieces of components, they'll start to develop red lip, is the name that it's called. The reason is dezinkification. So Typically, this happens when the metal has more than 20% zinc, because every alloy is a composite, right? It's a composite of so much copper, so much nickel, all this stuff jumbled up together and mushed together. The zinc portion, if it's greater than 20%, you'll start to see what's in this picture over time. And this is what happens when we definitely are not taking care of certain parameters. This being more prevalent and realistic to those that have galvanized metallurgies in their systems. That is why we bring this up. Although you might not see this in your cooling tower, for those that have galvanic basins, for those that have galvanic steels, dipped steels, treated steels, you have to think about this. And that makes it one of the ones that is fairly prevalent throughout our area. Okay, we promised to talk about stress corrosion cracking. A little bit of vibration and too many chlorides does not a summer make. And this is a perfect example of that. In failure analysis, we would be very interested to know if the crack occurred transgranular or intergranular. That would give us an idea of why it failed and what occurred. What we need to know about this is that if you have the right temperature, if you have the right amount of vibration, and you look at your system and you have too many chlorides, not enough of this, not enough of that, you will be susceptible to this in all your systems. Oftentimes, a little bit more so in boilers. However, we do see this in cooling water applications where exchangers have high temperatures. Okay? The last one, and I love saving this one for last because I find it hilarious. So, microbiological induced corrosion. Who knows about this? Get this. I thought it was a joke the first time I heard it. It was a long time ago, albeit, but I really thought they were screwing with me because I was the new guy. But bacteria set up shop right there. It ate something and it shit acid. Excuse the language, but that's what dug out that metal. The excrement of the cell, these susceptibilities walking right through and past this. At universities, campuses, maybe it's not the students themselves, maybe it's a visiting professor or some kind of family event that's occurring there. All these things are reasons why we should be attentive and make sure that our biocide programs are in place and effective as it relates to treating the cooling towers and making sure we do what we can to keep this at bay. The CTI best practice, for those that like fun facts for trivia, to keep Legionella at bay is 0.5 as a free chlorine residual at a minimum, 0.5 to 1 ppm free chlorine residual inside of an operating cooling tower. If we're doing this, that is going to give us our best shot at not finding Legionella present in the bulk water when we perform those tests. Okay? All right, let's go through a couple more fun facts. A progressive pneumonia is what Legionnaire's disease is, which when we say Legionella, obviously Legionnaire's disease is what it's called. It has a 2 to 10 day incubation period. It is usually treated with azithromycin. Household water systems can be guilty of creating and harboring this. And when you look at those that are most susceptible, it's like we talked about, those with underlying illnesses, elderly smokers, and I said 2 to 1, I screwed up, I'm sorry. I hadn't gotten to the slide yet in my defense. I told you it was sexist, 3 to 1, males to women. I don't even know how you generate that statistic, but that's crazy to me. Okay. Right? I guess. Because, well, yeah, we'll leave that there. But, so, symptoms include all the things that pretty much the common cold does. Makes it hard to diagnose. That's why you got to be cognizant of where you've been. If you think you might have been somewhere that had a dirty tower, or let's say that you are one of these people that might be susceptible, before you break into a cooling tower and perform some work on it, typically what we do for our clients is we'll go in and we'll clean it first. We call it nuclear bomb. We put it in there, we make sure that there's nothing bacteria-wise that could have lived, and then we drain it, we go in, we do whatever maintenance needs to be done. It's the best practice way, in my opinion, to make sure that the workforce associated with completing that task does not, in turn, have something happen to them that's not what you want to have, right? I mean, it's just no good deed goes unpunished as it is. Let's not make it worse. Okay. All right. Let's take a stop here and talk a little bit about the ways that we inhibit corrosion. We talked about our basic corrosion cell, anodic, cathodic areas, the free flow of electrons, and then that path always going from the anode to the cathode. It is our responsibility to find a chemistry that we can stick in the water that inhibits that corrosion from occurring. Like we said, we can't get rid of the water. We need that, obviously. We can't get rid of the free flow of electrons. That wants to happen if those two sites exist. But what we can do is we can block the cathode, we can block the anode. This, in conjunction with a sacrificial anode, makes you pretty stout when it comes to defeating corrosion from occurring in your system. Things in addition to this in your chiller systems would be epoxy coatings, or making sure that the grounding straps are appropriately connected where they should be. If you do have a system that is just really difficult, I've even seen nylon sleeves that the fasteners going from the channel head to the bell-end exchanger go through so that they can't help to create an electrical chemical connection there. So all those little things are very much the best practices of how to stop galvanic corrosion, electrochemical corrosion chillers, but specific to the chemistry piece, we can use anodic and cathodic inhibitors. Now, we used to use chromate in water treatment. Anybody seen the movie Erin Brockovich? Those people got paid. And they did so because chromate leached out of the retention pond at Pacific Gas and Electric, which I went to that site. They asked me to come look at it. I said no at first because I was like, there's some bad stuff here. I don't know. I'll help you remotely. What's that?
Used to mix it and put it in radiators on ships.
I know, right? It's terrible. But thanks to technology, finding out that yes, it did have an impact on health, we were able in the water treatment community to find a suitable replacement that, as far as we know today, won't do what the chromate did to people, cancer and different things. When you look at that, what you find is phosphate was the thing that the industry went to. So in a lot of your cooling tower chemistries that you find out there, you're going to have phosphate as the main corrosion inhibitor. It was economical and it had anodic and cathodic corrosion inhibition properties. For those of you that like to geek out in chemistry, that is a 2-for-1 deal that is hard to pass up. So when you can inhibit both of those and walk away with one bill, that's just smart. It got widely used. There are different kinds of phosphate. If pitting is your susceptibility for your system, pyrophosphate is a great one. There are different types of phosphates, is my point in saying that. Helping select the right ones for your system is part of what we do. Now, in addition to the anodic inhibitor capability of phosphate, you also have things like azole. Those smell kind of funny. They are definitely added to keep the yellow non-ferrous Admiralty alloys from corroding, in addition to watching your velocities. Okay, everything that I just said is on this slide. And so I do want to say one fun fact that's highlighted here is, I like to say this because it's just so darn counterintuitive. It's funny. We just spent so much time talking about not exceeding conductivity, not exceeding the saturation limits. We don't want scale to happen. Yet, when you look at how a cathodic corrosion inhibitor forms inside of a system on an atomic level, it is the precipitation of scale at the site of the cathode. And that's what's attaching to your sites that are all over the place, and it's blocking it. Doesn't stick around long, but it happens. This is why the basin exists in your cooling tower, because we know that over the course of your operational run, this is going to be occurring. You're going to suck in grass clippings because that guy can't drive past the damn cooling tower when they cut the grass the other way. These things, the composite effect, is going to give us a reason why we should expect to see conditioned sludge in our cooling tower basin. They should not be pristine at the end of the year. You should have to do annual cleanings on your cooling tower. And if you do have a pristine basin, you should be asking yourself why. Because all that schmooey is setting up somewhere in that system. And you should figure out where before it figures it out for you. We can help with that as well. Engage your water treatment experts in that conversation. Okay, I do want to go ahead and touch on deposition now as we finish the last 9 slides. If we look at this, for example, deposition control, we use dispersants. Now, we have one main chemistry that we typically feed that has all these actives in it. We proportion it so that as you cycle up the towers, the right amounts of each one are in your specific system. We have made our blends to match certainly this local area's water, and thanks to those concentrations, there's a bit of wiggle room we can do from summer to winter should the water change a bit, which it does in the river. And this is something that you should expect, a little bit of a different approach in summer versus winter. We disperse the particles using that chemistry, and that helps us modify the formation of those scale crystals. If you remember from the boiler presentation, for those that were here and awake, there was an under the microscope view where we looked at the sludge when it is conditioned and modified by the chemistry versus when it's not. It's jagged, it's crystalline, and it just stacks up a lot faster. That's the same kind of technology that's here. It's just utilized in this system, which doesn't get as hot. It still has the same benefit and still affords us the same opportunity to make sure that that scale does not become rigidly adhered to a surface we don't want it to be, allowed to exist, find its way to the basin, settle out, and then be blown down. Okay? Great. Everybody loves pictures. When we look at polymeric dispersants, we have to think of all these particles having a charge. That charge might be negative or it might be positive. What this dispersant technology does to anyone who's ever called it snake oil proves that it's not. It encapsulates this piece of particle, it neutralizes that charge, and allows them not to repel one another. They're allowed to come together, they become more dense, and then they can settle out in the basin. This is where the rubber meets the road and how that actually works. Okay? If you don't, then here's a different picture of a jagged, rigid scale that has not been treated or modified and how it stacks up, and this is what it will look like under the microscope should you not use a scale inhibitor, a deposit control agent like we were just discussing, that will go ahead and make sure that we don't build those crystals as fast, and will keep the small crystals that are newly formed. Sometimes it'll even redissolve them, and it'll help them go back into suspension, and you'll be able to cycle that cooling tower a little bit more before you run into making the scale. So the chemistry is doing a lot for you. In terms of these two actives, you're getting corrosion protection and you're getting protection from deposition. Okay? Then, if we look at this last picture, it highlights that. This is the jagged crystalline scale structure, and then treated, we have it distorted, modified. It's not allowed to agglomerate, connect, and build a stacked scale that will ultimately have to be cleaned and will cause you efficiency loss. Okay? Last stop on the train here is microbiological control, oxidizing biocides and non-oxidizing biocides. I love to end on a high note here. As a veteran myself, albeit Navy, not Marines, I like to use them as a foil in this example. If you think about oxidizing biocides as Marines, they just run in, doesn't matter if people are shooting or not, they just run in and they just blow up everything around them. That's an oxidizing biocide. It doesn't care. If it's there and it's bio, it's going to get burned by the bleach. This is the same as what you use in your laundry at home. Clorox, no different. And when you spill it on your hand next time and it feels a little slippery, remember that that's your skin turning into soap. We are bio, and you just put a biocide on it. That slippery feeling is your fingerprints going away a little. So, you have to respect these chemistries when you use them because they are on steroids in the industrial setting. And just because it smells like the same Clorox at home that isn't that bad, it is a little hotter in your plant. And if a biocide is leaking, you should definitely put on some gloves. Mind your eyes. For anybody that wants to see that next game or that next fight or whatever, you need to make sure that you're respecting these. The biocides are nasty. They're supposed to be. Like I said, the Marines are going and blow everything up. They don't care, and they will do it to you just the same as they will do it to all that sessile and planktonic bacteria in the cooling tower. Now, the non-oxidizing biocides, because we said we need more than one, so if we have two of them, like the Cooling Tower Institute of America says we should, to adhere to Legionella best practices, and we're rotating those biocides so that we don't have a strain of bacteria that is now going to be immune to the biocide, well, we're probably going to use something like isothiazoline or glutaraldehyde. Now, these are more like Hitman or Special Forces. They're surgical in nature. They mess with how a cell breathes or eats, and they distort that process and kill that cell in a way that is going to be a bit slower, 6 hours versus minutes, but it is going to stop those cells from multiplying and going on forward and creating numbers that are staggering. So you need your front line going out, rushing into the war, into the fight. But you also have a need to make sure that at some frequency, you're sending in the specialists and they're cleaning up everything that can't be gotten by that first line. Okay? Great. When we look at the Legionella best practice, I know I spoiled it for everybody a little earlier. 0.5 to 1 ppm is free CL2. This control range is safely above the detection limit for the meters that you guys would have access to, which gives you confidence that the number that you're testing is real. And then the target range is going to not only help you keep Legionella away, but let's talk about distribution decks on cooling towers for a second. When you lift up the hood and look under there, sometimes it's pretty nasty. It's real bad, especially if it hasn't been covered. There's going to be a lot of algae. By keeping this free chlorine residual always within your system, you're going to help to keep that from setting up and causing you issues that could restrict flow, stop your distribution from being even, and ultimately costing you in not being able to reject as much heat transfer as you go through the cooling tower. So, important thing to keep a mindful, hey, this is also good for this, eye on it. Okay? All right. Surface active agents and metabolic inhibitors, we just talked about it. Surface active agents are just one of those specialists that go in and distort or kill a cell a certain way. This is just a little bit of a fun fact there for the way that these things tend to work. If you look at it, the surface active agents will mess up the way that it can use the nutrients it takes in. And when you look at the metabolic inhibitors, it distorts the way that the cell can use that energy to then proliferate and replicate. Okay? All right. We're at the end. As sad as that may be, I think it's still prudent to review the training objectives. I think we did a decent job of understanding the goal of water treatment as it applies to cooling water. If we look at understanding how corrosion, deposition, and microbiological growth impacts a CT, just remember that trinity. I think that's a decent visual, that you can sink your teeth into and remember. We understand now that Legionella is even worse. It's 3-to-1, not 2-to-1. And we understand that the chemistry is a little bit more than snake oil. We now know that how corrosion inhibition works, the deposition control under the microscope, and why those biocides, no matter how bad they smell, are still worth putting into the darn system. Okay? So with that, any discussions or questions? If not, I wish you all a great evening. Thank you.
Thank you. Yeah, I remember putting sodium chromate.
Again, thank you guys for coming out. It's if you haven't taken one of these, please do. They're on the table. It gives you a list of what our training is going to be moving forward for the remainder of the next quarter, going into the end of September, October. I'm actually going to be instructing a workshop right after Train does theirs. Mine is more of a slide presentation. Okay, we're going to talk about hydronics. What I'm basically going to cover with you in my side of it at the end of this is a culmination of all of this, the boilers, again, open recirculating. It's not kicks and giggles, they call it an open recirculating system. Keep that in mind, okay? It's constantly working. It's constantly sucking in things. Locations of these towers are important, especially if they're near an interstate or something like that, chemical plant that you mentioned, ammonia. So be cognizant of where they're located and what they can do, and that will also dictate how often you get it serviced or cleaned. Gearboxes, he mentioned, are very, very important. Help them help you, okay? When you have a situation like that, don't, hey, we're all human, okay? We all had to learn, right? So look at it from that perspective. Communication is the key with this, okay, guys?